New magnetic motor breakthrough. 0% friction and 100,000 plus RPM. Imagine a machine that can spin faster than the turbines inside a jet engine, yet never actually touches itself. No grinding surfaces. No slow erosion of metal. No whisper of friction stealing energy with every rotation. For centuries, engineers have accepted friction as an unavoidable law of motion, the quiet tax every machine must pay simply to exist. Bearings were down, heat builds, efficiency drops, and eventually everything fails. It has always been the cost of mechanical progress. But what if that cost could disappear? Somewhere at the edge of modern engineering, a new kind of motor is challenging one of physics' oldest limitations. It can rotate at over 100,000 revolutions per minute, a speed so extreme it almost defies intuition, while promising a lifespan dramatically longer than the machines we rely on today. No constant lubrication. Fewer moving parts to degrade. Almost no mechanical wear at all. On paper, it sounds less like an upgrade and more like a violation of the rules engineers have worked within for generations. Naturally, this raises unsettling questions. How can something spin without touching anything? How does it remain stable instead of tearing itself apart? And if this technology is truly as transformative as it appears, why hasn't it already replaced the motors inside factories, hospitals, and transportation systems? The answer begins with a concept that once felt closer to science fiction than practical engineering: magnetic levitation. Instead of fighting friction, this design quietly removes contact altogether, allowing the rotor to float in a carefully controlled magnetic field. And yet, if the impossible motor is already here, capable of redefining reliability and performance, a deeper question emerges. If this technology is so revolutionary, why isn't it everywhere already? Friction has always been the invisible adversary of progress, a force so familiar that most people never stop to question it. Every rotating machine ever built, from the roaring turbines of aircraft engines to the silent precision of a hard drive, lives under the same quiet sentence. Eventually, contact leads to decay. When two surfaces meet at high speed, the consequences are unavoidable. Heat begins to build, microscopic fragments of material shear away, energy that could have produced motion is wasted as resistance, and what once operated flawlessly starts drifting toward inefficiency. At first, the damage is almost imperceptible. A fraction more vibration. A slight rise in temperature. But over thousands of hours, friction writes its signature into the machine itself. Components warp. Clearances widen. Performance drops. Entire maintenance industries exist because no matter how advanced our technology becomes, moving parts are always fighting a slow battle against each other. Human ingenuity, of course, refused to accept this limitation without resistance. Bearings emerged as one of engineering's most elegant compromises, small, deceptively simple devices designed to reduce contact by replacing sliding friction with rolling motion. It was a breakthrough that powered the industrial age and made modern machinery possible. Yet even the most sophisticated bearings, engineered to astonishing tolerances, cannot escape the fundamental truth: they are still touching. Lubricants degrade, surfaces fatigue, contaminants infiltrate, and sooner or later failure arrives. This leads to a realization that is both humbling and profound. For generations, engineering has never truly eliminated friction. It has only learned how to manage it. Now imagine stepping outside that centuries-old strategy entirely. Instead of minimizing contact, what if we removed it altogether? The magnetic motor represents one of the first serious attempts to do exactly that. But this introduces a new and unsettling challenge. Can something truly remain stable while floating? At first glance, magnetic levitation feels less like engineering and more like a controlled suspension of reality. We are used to objects resting on something: a table, the ground, a support structure. Remove that support and gravity takes over. Yet magnets introduce a strange alternative. When opposing magnetic fields meet, they push against each other with invisible force, strong enough to lift weight into the air. No strings. No platforms. Just fields interacting in perfect opposition. It sounds elegantly simple. Let magnets repel and the object floats. But this is where intuition betrays us. Magnetic systems are naturally unstable. Try balancing a pencil perfectly upright on its tip. For a fleeting moment, it might hold, but the smallest disturbance sends it tumbling. Early levitation experiments faced the same dilemma. A rotor suspended by magnetic force doesn't politely stay centered. It drifts, wobbles, and threatens to snap out of position. Floating, it turns out, is far easier than controlling what floats.